Cool. Here's what I had. What? You know what? That's research. Yeah, you should ask me. You should get in class. Actually, take a look at me. Third, that's what I thought. Oh, so you're gonna major with? We'll do the major. Let's do. I don't think they do it as well. I think they have. It's like what I don't even get. It's like 30 hours. It's like not even minor. Whoa, whoa, like a freak. Yeah.
No,
It looks really good.
no, nothing.
Well, I think high schools don't like saying.
So for this one, I'm wondering, did I do something wrong, or is that how we did it in the class? So for the we're supposed to find the E cell, right? Calculate the E cell. So if the E cell is this number, so we already have the E cell. So why did we put it here? Isn't it supposed to be here?
This is E not cell. That's E cell. So E cell is actually tied to your E not cell plus 0.025693 times your ln cube.
So this is not the E cell. This is the
So every time I put a little circle on the top right corner, you don't ignore it. That's the things to distinguish this from that. So E cell, see, there's actually no little. There should be actually little circle here. It's actually the one without.
Okay, yeah. Because I was confused why we did it 2 times. Okay, thank you.
I would say like. This is how you've ever done this. Oh. I bet you have them like this. Oh, you like literature stuff? No. I agree. Right. That's all I'm from the session. I agree with it. So if I put your rating for basically more, I think it's we told you what? Why would you insult him like that? To be curious. I think not. Like I can see it on math. I don't think math. I can see it on math. Yeah. Like when I see math, I'm like, damn, I could definitely do that. I think so long like no, I do like it. I just don't understand why it's like what's the no, I guess it's a what? This guy's up to the guy. Yeah. So you're staring at him while he's it's crazy that you know.
Okay, so any questions before we get started? So today I have actually gone to a meeting earlier, so we can actually move our office hours slightly. Okay, so instead of starting at 11, we'll start at 10:30 today. All right, so what we are going to do today is try to finish second chapter 17. Okay, and then going to discuss today will be if I give you an aqueous solution, if we do the electrolysis, what will be the product you're going to see either on the cathode or on the anode. So that will be actually the first thing we discussed today. Then we'll actually move to the second topic, which is topic 18. Then we're going to show you how to write an atomic symbol. Okay, and based on the given atomic symbol, can you predict whether the atom is stable or non-stable? Okay, and if it's non-stable, then what kind of decay this atom is going to undergo? Okay, and what direction turn out to be? So those are the main focus of today. Okay, so very simple stuff starting from now is really, if you know it, then you know it. Okay, there's not much like complicated calculation involved. Okay, it's more like you just need to understand the content, and then you should be able to actually address all of the questions afterward. Okay. So first thing first, just a refresh of our memory previously. So at the end of the previous lecture, we start to describe. Today I do electrolysis, meaning you put in using a big battery, trying to create some electrochemical reactions within the beaker, right? And then we tell you if you have electrolysis undergoing, here I move to the cathode, and I move to the anode. Okay, and then at cathode, you have your G-rock, meaning that the species, the here will undergo a reduction reactions. Okay, so you're going to deposit loadings onto your electrode on the cathode. Anode, on the other hand, your ionic species, your anions undergo an oxidation reaction, which provide electron to your electrode, and then go to the wire and go to your battery to form the circuit. Okay, so on your anode, you have your LoRa. Okay, and the things that to predict what kind of species that's going to be electrolyzed on your cathode and anode. There's three different layers of complexity. The simplest one is just a molten salt, right? Meaning that inside your solution you only have cation and anion. Okay, so if you do that, and under the electrolysis condition, you're going to see the cation are reduced form on your cathode, and the oxides form on your anode. Okay, so that's actually a simplest case. Okay. The second case is called a mixed molten salt, meaning that you put two different types of salt into your beaker and then raise the temperature so it also then become melt. And then you put in the electricity and try to figure out who is going to form first on your electrode. Okay. So the way we actually make those judgments is actually by looking at, we're actually looking for the last negative reduction potential or last negative oxidation potential. Okay, again, if you're actually looking for the things on the cathode, you know it's zero. Okay, then you should actually use the reduction potential. If you're actually on the anode, which is your LoRa, then you're looking for the oxidation potential. Okay, so if you compare the two salts, whoever whose cation that has less negative reduction potential will be the species you're going to see on the electrode. Okay, so less negative is actually the things that we're going to pay great attention in the next 10 to 15 minutes. Okay. So that's actually the second condition. The most complex condition you're going to encounter for this electrolysis question is that you have aqueous salt solution. Okay, because besides the situation we discussed previously, right now you have another molecule that you have to consider, which is your water. Okay, so if you have aqueous solutions, And when you're trying to compare your reduction potential E naught or the oxidation potential E naught ox, the E naught and E naught ox for your water need to be taken into account. Okay, so if your water undergo a reduction potential, okay, every time I say one things or one molecule undergo a reduction potential, you should have an idea that equation-wise, what it means is actually you add in the electrons, right? So you need to know when the water gets electron, what it is going to produce. Okay, you will need to actually, I would suggest memorize this. The reduction potential of your water will be your H2. Okay, and then the reduction potential is negative 0.83 volt. Okay, so this means if today I'm going an aqueous salt solution, let's say aqueous sodium chloride solution. Okay, and then I try to figure out what's going to form on my capsule while doing my electrolysis. Okay, so the slope flow should be like this. Since I'm talking about capsule, right, in the of an aqueous salt solution, then the species I should pay attention will be the ions and water. Okay, so that's the things I want to practice. Every time you see these things, okay, what's going to form on the capsule? Then you should respond with, okay, I should look for ions and water. Okay, then what you do? This is in the capsule, right? You actually is zero, so reduction. You actually looking for the reduction potential. Which species, whoever species has the less negative reduction potential will be the species that electrolyzed first. Okay, so that is actually really basic logic. If you follow that line, when you read the question, it's very easy to actually see the answer. Okay. On the other hand, if today I'm asking what the product going to form first on the anode, right? Then you should actually, the things you should have in mind is that since we're talking about anode, right? So Laura, the species that can actually undergo oxidation reaction. Okay, there's actually an anion that you care about. So looking for the anion, okay, and looking for its oxidation potential. Okay, and then compare that to water. Okay, whichever is less negative, less species will be the product on your anode. Is that clear? Everybody follow the logic here? Yeah, so that's the things you need to actually have. So every time you read the question, you know what to do immediately. Okay, so again, I keep bragging about my LoRa and G-Rock, right? You see that again here. Anode, LoRa, right? Oxidation. You need to actually look for your inner ox. G-Rock, reduction. You're looking for the reduction potential, right? At the castle. So you really have to get used to that kind of thinking. That every time you read the question, you feel like, okay, you know exactly how you should actually proceed to solve the problem. Okay. All right. Before we go into examples, okay, before it goes to examples, I want to really memorize the product of water. When you undergo reduction, the product should be H2. If it undergo oxidation, the product should be O2. Okay. And the E naught and the E naught ox, I would suggest you also memorize it. Otherwise, you always go back to check the table. Okay. So y is negative 0.83, that's negative 1.23 volt. Okay. Okay, so let's look at this. So it says, in the electrolysis of molten lithium bromide, which product will form at the anode? Okay, what are the keywords? Yes, electrolysis. Okay, that is actually keywords, right? The Q is actually you want to find out the product on the at the product at the anode, right? So every time you see anode, you know the things that matters is your LoRa, right? So it's kind of like you should have those like instantaneous response. It's anode, so I'm actually looking for the LoRa. Okay, but this one's actually simpler because it's just a molten salt, right? So the data tells you the salt you have lithium bromide, which I know you know once they melt, okay, they will exist in the ionic form. Okay, so lithium is always +1, right? Bromide -1. So lithium plus Br minus, that's going to show up in your solution. Okay, and then when you do the electrolysis, Ka goes to cathode, Ni goes to your anode. Okay, so by doing this simple analysis, then you should know you care about the anode, right? So you know the Br has undergone oxidation. Okay, to form the product at anode. Okay, so your Br is going to lose its electrons, Br minus, forming Br2 plus 2 electrons. Okay, therefore, for this one, it's very simple, right? Since you only have one single NIR, then less species, once it oxidizes, will produce the product on your anode. Okay? So any questions on this? We good? Okay. So what will be the things on your cathode? What will be the species showing up on your cathode? The Ka, right? So the reduction of the Ka, right? What will lithium plus become after they got reduced? So Li plus 1 electron, right? So it becomes lithium metal. Okay, just simple Li. Okay, so I know some of you will be like, okay, how do I know all this? Okay, so when you do your midterm 3 or when you do your homework of quiz, okay, very often you're going to see a table like this. Okay, you're going to see something like that. Okay, so you need to actually learn how to read this table, and it's actually very useful. Okay, so let's focus on the things here. Okay, look at the line I just highlighted. Okay, so what do you see there? It's a lithium plus 1 electron. They give you lithium, right? So apparently this is actually a reduction reaction. Okay, I hope everybody
understand that, okay? And the reduction potential is what? Negative 3.04 volt, okay? That means when you try to do the electrolysis of your lithium chloride, if you want to just see the reduction of your lithium plus and to supply 3.04 volts electrons that goes into your solution, then this process will happen. Okay, that's what it means. Okay, so when I ask you what's the product at the cathode, right? You know you're just looking for the K, therefore you know you are looking for lithium plus, right? But that is not your answer. It is actually after the reaction. That product is your answer, right? So if you look at this table, I guess since you have the equation, it's very easy for you to identify what the product is. Okay, and input that into your answer, then you will actually get the credit for that. Is that clear? Okay, so you usually learn how to use this. Okay, let's do one more practice. Okay, so the one I just highlight here, manganese 2 plus 2 electron like your manganese. Okay, so you should actually see that if my manganese 2 plus undergo a reduction potential, every time it's right at plus some electrons, right? Read it as undergo a reduction reaction. It's going to produce what? An magnet. Okay, and it requires how many volts? It requires 1.18 volt to do your electrolysis. Okay? So everybody fine with the things I just said? Okay. Next question. If today I have the mixed molten salt, where the 2 ions is lithium plus and manganese 2 plus, which things I'm going to see first when I do the electrolysis and my cathode? Manganese. Okay, because the manganese requires less volt to get reduced. Okay, so remember I say we should always looking for the less negative potential. Okay, that's what I mean here, right? You can see that Mn2 plus require much less volt to get reduced. Okay, so that is actually the things I want to emphasize. Okay, is that clear? Okay. This guy is what? This specific reaction says the reduction reaction of water, right? What's the voltage you need? You need 0.83 volts to reduce your water. Okay. So now let's say I have an aqueous solution. I have an aqueous solution that contains lithium plus, that contains Mn2 plus, that contains Mg2 plus, that contains Ca2 plus. What's the product that I should see on my cathode? What's the product I should see on my cathode? Okay. So previously, we compared these two, right? We compare lithium plus and Mn2 plus, and ask you which one you're going to see at your cathode, right? And then I guess most of them actually responding with that Since the NN has less negative reduction potential, therefore I can see NN solid on my cathode. Right? That's the things that I got from you guys. So now we actually make things even more complicated. Right now we have 3. I have an aqueous mixed salt solution. Okay, meaning that I have H2O and N2 plus and lithium plus. What's the product I will see when I do my electrolysis at the cathode? Yes, the answer will be H2. Okay, so what the things you can use for judgment is that whoever has less negative potential, the product of that will be your answer. Okay, so here apparently the product of your water is what? This guy, right? Okay. One more. Now I have 4 species now. Okay, you have your lithium plus, N2 plus, H2O, and Cr3 plus. What will be the product you're going to see at the cathode? I think most people now see this, right? Since this guy has the less negative potential, therefore the product, the reduction product of this guy, which is your Cr, right, will be the answer. Is that clear? Okay, everybody get what you need to look for now? Okay, so this is actually easy because the default is what? Reduction potential, right? Okay, so I said up to this point, everybody understand what I'm looking for. Okay. So everyone have a good sense about we're actually looking for the things that's going to form on the cathode under electrolysis. It's very simple, right? Just looking for the reduction potential. Whoever is actually less negative, they will the product of less. The reduction product of that reactant will be your answer, right? Now we have to flip the coin and talk about what? Oxidation. This is all reductions, right? So then we have to do the oxidation. Okay, so what happens when we do the oxidation? First, all the equation will be what? It will be flipped, right? So let's use this as example, okay? So Pb2 plus 2 electrons to Pb. Then you have a reduction potential of negative 0.13, right? But if today I want to figure out the oxidation potential, what you do is actually flip your reaction, right? Then you have your oxidation potential, and then the value will equal to. Okay, so this will be needed when you need to do you won't find the species on your anode, right? Because once you see the anode, LoRa is the things you're just looking for, right? Once you see the LoRa, then you need to use the oxidation potential instead of the reduction potential. Okay, but your textbook or your exam will only provide you the reduction potential. Therefore, you have to first generate your own oxidation potential table. So you can use the same principle to make the judgment properly. Okay, is that clear? Okay, so do that, then you can actually answer the things correct every time. Okay, so once you have the oxidation potential, okay, then if I ask you what are the species you're going to see at the anode under electrolysis, okay, then you want to figure out the one who has the less negative enough oxidation. Okay, and find out the product of that specific equation, that will be your answer. Okay, is that clear? We're going to use the question to practice that. Okay? Okay, so if you can see this type of question become actually very easy for you. You just check the table and you will know whether that is actually the answer you are looking for. Okay. So let's do the question number. Okay, so this is actually a very standard type of question you're going to encounter. Okay. So the statement is like this: hydrogen can be prepared by suitable electrolysis of aqueous rubidium salt. Okay. What's the keyword here? Apparently, electrolysis is so important, right? Because every time you see the electrolysis, then the things we just described in the past 5 minutes should pop up. Okay, you're just looking for the last negative, either oxidation potential or the reduction potential, right? So now, the other keyword show up here is the hydrogen, right? So hydrogen and oxygen are the two unique molecules when you do the electrolysis of water, right? So what this tells you is that you want to compare the reduction potential of water, okay, to certain species, right? Because H2 is actually the reduction product. Therefore, you know this is actually a reduction of H2O, right? So this is actually reduction. Then you know the things you should look for is actually your G-rock, right? Reduction, right? In electron, you undergo a reduction, right? So you know you need to actually do the G-rock. And this thing will actually go at which electron? N or cathode? Cathode, right? G-rock, the very last letter for your G-rock is cathode. Okay? So this is cathode. Therefore, you are looking for the reduction potential of all the K ions inside your solution. Okay? So with all this knowledge in mind, when we read this question, do you notice that it only tells you the rubidium salt, right? So what is rubidium? Every time you see these things that you're not so familiar with, what do? Check your periodic table. Okay? So anyone have periodic table? Okay, can you tell me where rubidium is? It's actually the 1A element, right? Then you know over the charge of less salt. It will be rubidium 1 plus. Okay? Therefore, you know the cation you are looking for is what? Okay. So right now, what do you do? We are going to compare the reduction potential of rubidium plus and H2O. Okay? So then what you do is actually you go back and check the table. You have it here. Okay, my table is actually not big enough to contain the rubidium. Okay, see if I check it out previously. Oh, I do. Okay. So the data that you have is that you have H2O, you have Rb plus. Okay, and then it's undergo a reduction reactions, right? So this will give you H2 plus 2OH minus, where we know the reduction potential of water is negative 0.83 volt. Rubidium, on the other hand, if you have a complete list of the reduction table, you'll be able to find that the reduction potential of that is, okay. So apparently that the reduction of the rubidium class into rubidium, it has much, much higher voltage, right? Therefore, you know, the species is going to be electrolyzed and then show up on your castle will be your H2. So the answer will be yes, that is true. You are going to see the H2 will be formed when you do the electrolysis of aqueous rubidium salt. Okay? Any questions for this? Yes. Yes. Okay, so at the midterm 3, you're going to have a big chart in the front right next, I believe, right after your periodic table. Okay, so don't worry about memorizing all this. What's the reduction potential of that? No, they will be provided. Okay. Sometimes they actually provide in a semi-clear way. They just give you the reaction product and then they give you the reduction potential itself right now, the full equation. Okay, so you have to know every time you see that is reactant product and then the reduction potential. Okay, otherwise you actually give you a full table and everything will be just the same, exactly the same what we do here. Any other questions? You good? Next questions. Okay. So the question says what? The oxygen can be prepared by suitable electrolysis of aqueous perchlorate salt. Okay. Again, keyword electrolysis and oxygen. Okay. So how can we actually learn from here? First, we know oxygen is the oxidation of H2O, right? So the oxidation product of H2O is O2. Reduction product of H2O is H2, right? So as you see oxygen here, then you know the process you're talking about is your oxidation process. Okay? That means you're looking for lower, right? Meaning the things that is going to show up in your anode. Okay, so those are the things that you should have, right? And then you should actually looking for the less negative oxidation potential. Okay, so these are the original concept from the previous questions, right? Okay, so then you want to look for, okay, what are the NaN you're going to use, right? So here, you know, one plane is actually H2O. It's undergo a oxidation reactions, right? Therefore, it's going to load its electron, produce H2 plus 4H plus 4 electrons. the oxidation potential is negative 1.23 volt. Okay, so this is actually the oxidation equation of water, which I suggest everybody memorize it. Okay, so the reduction. Yes. Thank you. Okay, so make sure you memorize the equation, right? The oxidation and reduction of water and its corresponding reduction potential and oxidation potential. It's very useful. Okay. So let's actually first things that you need to consider, right? The other things you want to consider is what? The NIM, right? So what's this? Perchlorate. ClO4 minus. Okay. Okay. So every time you see this multi-atom NIM, okay, they are very, very electrochemically stable. Okay, meaning that if you want to actually oxidize these species or reduce these species, you need to go to a really, really, really high voltage. Okay, so of course you can check our table and then find out the numbers. But typically, when you see these multi-atom anions, they are not going to undergo any redox reaction. That means they are not going to change. Okay, a few multi-atom anions. I will list a few very famous ones. Okay, so like this ball, if you see that show up in your redox reaction, ignore them. Okay, meaning that the voltage they need to actually undergo a redox reaction is just way too high, and no one really wants to measure it. Okay, you want to find the. I don't think you're going to find any reduction potential or oxidation potential of this species in the table either. Okay, so if you don't see those information, just they are not undergo any changes. Okay, so the next actually we're going to do the electrolysis of this aqueous perchlorate salt solution. Okay, and the anode is equivalent to just electrolysis of water. Okay, therefore, you know the product will be your oxidation product of the H2O, right? So you're going to have the O2 forming at the anode. Okay, so that's actually how you address this question. All right, concept-wise, it's exactly the same as previous one. But previous one we used the reduction reaction. This one we start to talk about the oxidation reaction. Therefore, the potential you're looking at is different, right? Previous one we look at the reduction potential. This one we are looking at the oxidation potential. Is that clear? Okay. Okay, so question number 8. It says, what product forms at the cathode in the electrolysis of aqueous solution of K3PO4? Okay, what are the keywords? Electrolysis is the first one. What else? Cathode, very good. Cathode is a keyword. And aqueous solution of lead. Right? So why these are keywords? Because you know it's actually about your cathode, right? You know the things you're looking for is what? GROC, right? GROC means that the things happen at the cathode is like a reduction reaction, right? Therefore, you know you need to compare First, let's try these things. Okay, cathode. So the species you care about is ions and H2O because you have aqueous, right? And then the things you want to actually looking for is your reduction potential. Okay, so whoever have the less negative reduction potential, that will be the reduction part of the species will be your answer. Okay, so let's actually the first line. Right, then we can actually do the Q. We want to know the product at the castle. Okay, data. Since we only care about air and water, right? So we can actually write out the water. Okay, so H2O, once you undergo reduction reactions, and then you should have your reduction potential equals to negative 0.83 volt. Right, so that's actually the first species we want to write. The second species will be the chaos that showing up inside your solutions, right? Then you start to look for what other things that you have. You have K3PO4, okay? So by now you should see that this will be becoming 3 potassium plus PO4 3 minus, right? I only care about the chaos. Therefore, you know, all you want to write is this. And then you can check out its reduction potential, which is that value. Okay, so you go and check out the table and you figure out, okay, that's the value you're going to put over there. Okay, so you have H2O, you have K plus. Also, you can undergo a reduction reaction, right? And then you have the reduction potential drop here. And you pick up the one with less negative reduction potential. In this case, will be your H2O. Therefore, you know the product at the castle is H2 and OH minus. Okay. Any questions? Everybody fine with this? Okay. So I want to ask you one more thing. What will be the product at anode? What will be the product at anode? O2. Right. So how do we figure out it's O2? Because it's actually an anode, right? We're actually looking for the anions and water, right? The oxidation part of the anion and water. What the anion do you have? PO4 3 minus, right? I just mentioned that in the previous questions, right? We have this multi-atom anion. They're just way too stable. Then I can undergo the redox reaction. Okay, therefore your only choice will be your water again. Therefore, the oxidation part of your water will be your O2. Okay, so if you have those concepts in mind, you should be able to actually address this question very easily. Okay, so all the things you need is actually really follow the problem logic flow, so you can actually resolve this question like please, right? It's just it's for me it takes very basic no time to actually figure out the answer. Yeah, so your question is that we need to actually this actually answer H2 and OH minus because when you undergo this, you produce H2 you also produce OH ions. Yeah, so both will just show up in the electron. Mhm. Any other question for this type of question? So if not, that's actually the very last question we'll go through for chapter 17. E. Okay, the second part of chapter 17. Okay, so in this second part of the chapter 17, we only talk about very simple things. Okay, first we actually connect the cell potential in a cell to the equivalent constant K. Okay, so there's actually a few questions. We're going to do this. We're going to review all these equations next week. Okay, but I want you to actually start to do these things on your end. Okay, so the most efficient way that you can get most out of the lecture is that you come here with some understanding of the material. Okay, then I will actually keep poking you and telling you, hey, this is really important. You need to reinforce those important things. Okay. Yeah, so we talk about that, how the enough cell is related to your equilibrium constant K. Okay, then we have another equation about how the in cell is related to the chemical quotient Q. Okay, and then after that we have this equation tell you once you do the electroplating, this is the same as your electrolysis, but just the reduction part, that the metal will deposit onto your electrolyte. So you have this equation, grain of your product will equals to n times second divided by number of electron transfer between your LoRa and GRA divided by your fairly constant times the molecular mass of the product. Okay, and after that is the things we talk about today. Predict the product at either the anode or cathode for electrolysis reaction. Okay, so those are all the content we went through this week. Okay, so we spent so much time after we actually try to summarize it. It's like 2 minutes. Okay, so it's much easier than the midterm 2, right? For midterm 2, we emphasize so much, so you can just see what solution that you have, right? Strong acid, weak acid, strong base, weak base, proper titration. There's a lot more complicated things going on there. Okay, but you guys handle that pretty well. Okay, so you should really use this opportunity to boost your grade. Okay, so you should actually just study like how you study your midterm 2. Okay, put in the same amount of time and effort. Okay, prepare early. Then I think that will actually greatly help your midterm 3 score. Okay, one thing I found sadly in the past experience is that typically my section will do much better than other sections in midterm 2. Okay, meaning that on average you probably have to beat other section by 5 points to 10 points. Okay, this time I think we did probably up to 10 points compared to other sections. Okay, but typically what I see in midterm 3 is that if that was second time is what we have achieved, then the average of my midterm 3 is always lower than other sections, which I don't quite understand. Okay, yeah, the only explanation that I have is that if you're like, okay, I'm good. Okay, then I spend less amount of time. Okay, then I'm not organized for my midterm 3. Okay, so please don't do that. Okay, so I'm a person who respects students' efforts very much. Okay, so in order to do really important things in the future, you want to actually finish something from the beginning to the end. Okay, I know sometimes we all get lost in the beginning, which is normal. Better guys like my performance when I was very young. My sucks, Okay, so I guess we have some time today, so I will just talk about that maybe for 5 minutes. Okay, so I was actually originally from Taiwan. Okay, and when I go to my college in the first year, I can't be like, okay, I'm a grown up, I should be able to do what I want to do. So I hang out with my friends so much. Okay. And I like to do karaoke so much back to that time. Okay, we have 60, I have 60 classmates. Okay, so chemistry major, 60 classmates. Okay. In the first year, I'm very able to my chemistry. Yeah, sorry. Okay, my professor is not like attractive either. I mean, why is attractive is actually he says something that's, you just read the textbook. I don't like it, right? So I can read the textbook myself too. Okay. Of course, I was cocky too, right? So, you know, I feel like I can do everything I want. Okay. So after, you know, all this abuse of my time for a semester, so I finally got my transcripts, right? And to put the transcript back to home, so that, you know, mom can take a look at it, right? When I received my transcript, I'd be like, okay, my God. And I actually bring this back to my mom. Feel quite so much. Okay. So I ranked like 55 out of 60. Really, really bad. Okay. So I don't have that much feeling back to that time. Okay, if I was young, I feel like to know someone back to me telling you guys the things that I experienced in the past. Okay. So in the first semester, sure, I will do better next time. Okay. And still doesn't really change how I behave. I still checking out a lot with my friends. Okay, I still go to all this activity. Then business continues. Okay, I was doing really bad for the first year. Okay. Yeah, and you know, the time will eventually come, right? My mom eventually will see the transcript after a year, right? And when she saw the transcript, she didn't say much. She just said to me that, oh, I guess the course is just really difficult. Okay, so do your best. And I feel like I'm ashamed of myself because I don't really interact with. Okay, so I went with this university, of course, that's a top university in Taiwan. Okay, I was actually a very good student when I was in the junior and senior high school. Okay, but once you go to that top university, everybody has very similar background. Everybody's actually very good, right? So after the first year, I started to feel bad about how I behaved in the past, and looking back, the time is gone already, right? So I tried to catch up, right? But I realized, oh gosh, that I lost so much knowledge that retaining is actually become difficult. Okay, so I do improve in the second year. I guess I go from like 55 to maybe 20 or 30 of the class in the middle of the class, right? Yeah. And the thing that changed my mind the most is that my mom is truly believe that I can do great things. Yeah, the true support of the family is really amazing to me. Okay. So when I enter my junior year, I decided to transform myself. Then I become a person who only go to three places. One is actually my home, one is my classroom, the other place I go in my third year is library. Okay, I typically spend like 8 to 10 hours in the library in my junior year. I only do study. Okay, at the time I started to write open notes for all my courses. I handwritten notes. Okay, and that's how I realized I become very good at it. Okay, so I think I took the inorganic chemistry back to that time. Yeah, because I opened so much things, I become a tutor for my class. So I gathered like around 10 good friends of mine. Okay, I tell them, okay, this is actually my note. Then they start to print my note and share with everybody. Okay, so at the end of that semester, because I spent so much time and effort into the inorganic chemistry, I tell them I feel like I can predict what question will show up in the final exam. Okay, so I guess like 10 questions. Okay, 6 of them actually show up in the final exam. This time, like, okay, I know how professor think. What are the things that they want us to learn, right? So that semester, I think I have a huge transform. I go from like 20 something to number 5. Yeah, not bad, but still not the top, right? So I continue doing this, and then if I do so well in my organic chemistry, my professor asked me out, am I interested in joining his lab doing some research? So I said, sure. Then I took a master, I believe. Okay, so I graduated with the first place for a master degree. Okay, so no, I'm just sharing this with you because I want to let you know that yes, when we're young, we all make mistakes, right? But I know what I want, right? I want to actually be some person that has some impact, and I do appreciate the people who help me along the way. Therefore, when I was very young, I feel like I should be a teacher. Okay, and I do like research. So I want to become a researcher in the world. Okay, so that's why I decided to come to US. US has the best research program in the world. Okay, so we have the most resource to do the things that we want to really do and try to actually explore some new knowledge in the world. That's the things I really like. That's why I'm here, right? So after I graduated from my master's degree, I actually went to the first school in Texas A&M, College Station, very close by. Okay, and then after that, I do my postdoc at the Cornell University, New York, Islam. Okay, and then I feel like along the way, I always encounter someone that's so wonderful, tell me how to think, how to make a better me every day, right? So I work very hard. Okay, because I do see how my effort becoming something that I can be impactful, that I can start to influence the younger generation so they can actually understand how things work. Okay, but it takes time, right? So it sounds actually a interesting story for the student. Okay, but you need to know that's actually every day, 10 to 12 hours for years. Okay, not just for a week, for years. Okay, I'm still doing very similar things even now. After I become a professor at my Tai-Yen, right? I still just spend a lot of time doing my research. Okay, I typically come to my office before 6 a.m. Okay, and I will leave at 5, so I can actually go back home and play with my kids. Right. So that's why I say to students, okay, I do respect your efforts. Okay, but sometimes I feel like the effort that you put in, okay, how does it actually compare to the effort I'm actually talking about? I feel that's actually yeah, right. Because when I say, okay, I really put in my effort trying to make things work for myself. Okay. I know everybody starts to talk about the work-life balance, which I totally understand. Okay. So let's actually Mr. come to me and ask me about like, how do you actually balance your work and life? I was telling them, like, I'm super balanced. Okay. And they say, oh, you work very long. And I say, yeah, but that's actually life I'm looking for. Right. So I want to be doing my research, I want to bring new knowledge to the world. Okay, I want to spend time with my students so I can teach them how to think properly, not just for specific course, but for their life. Okay, I also enjoy the time I spend with my kids. Okay, I want to actually listen to what happened in the school. I want to do the homework together with them. Okay, this all takes time, right? So if you just use time to value the work-life balance, it's not very accurate, right? Because if I'm doing this, I enjoy it. I feel I'm totally balanced, right? When would you feel you're unbalanced? You will force to do something that you don't really like. Does that make sense? Okay. If you actually doing something that you know that's the things you like to do, it's very easy that you spend a lot of time on it. It's really easy, right? But do you feel unbalanced? No, you feel you're totally fine. I feel like, okay, my daily routine is totally okay, right? But someone else looking from from the other side, looking at, okay, this one is like a workaholic, right? But you care. You shouldn't, because they are not you. They are not living your life. You are the one that live your life. Okay. When I talk to my son, okay, you say, okay, something happens. Okay, but that's not my fault because blah blah blah. Then I say, I thought you are your own boss. Then he's like, but you just shut, because you know. Because every time you want to claim he's his own boss, then be responsible, take the consequence. And no matter what we do, there's actually consequence. Okay, are we actually brave enough to take the consequence? That's very important, right? When we are young, it's very difficult to actually be brave enough to take the consequence. But as we grow up, there's something you cannot avoid. If you avoid it, you're actually digging a little hole in your own worth. You're not going to achieve the dream you always had. Okay, so I always tell my son and my daughter, okay, net the educational gaps and do it, okay? Don't be afraid of errors. We all make mistakes. I make a lot of mistakes when I was young, right? Everybody says that now, okay? But if you truly believe you're actually moving toward your dream, then you're actually getting braver along the way, and you are persistent, you are resilient, okay? You're not going to be defeated by the failures, then you will be fine. Okay, so we all learn all the rules that work around us. Everybody has different experience, therefore everybody has different sets of rules. Right? But whoever can master the rules around you, typically will live pretty good life. Okay? So come back to here, right? The things I want to really emphasize is that we all need to practice how to put in an effort. And this thing is not easy, but I want you guys to try. Because once you're actually good at it, you can really achieve many things that you don't believe you will achieve in the past. Okay, so do have a plan, do have a target. Okay, if you have someone that you believe is knowledgeable, talk to them, make yourself grow. Okay, and make yourself great. Okay, whatever you do, there's actually a consequence. Okay, I am a person. I don't think I regret things that I did before, even that may actually bring me very negative results. Because I know when I make those decisions, I tell myself, okay, this is actually the best decision I can make. No matter what the consequence is, I will take it. It's good, great, move on. Bad, suck it up, cry a little bit, and move on. It's okay. Okay, so I want to share with you about all this my personal experience. Okay, and hope this will actually help you along the way a little bit. Okay? Okay, 10 more minutes. All right, so we need to actually start to talk a little bit about the chapter 18. Yeah, because I'm not quite sure how much I can actually deliver today. Okay. I think we are good. Okay. What about we'll finish this one next week? Okay. So chapter 18 is all about atoms. Okay. So humans study atoms for a long time. I want to share you with this little clip, little picture here. Okay. Back to 1903. Okay. So the first person who bring up the idea of atom is Dalton. Okay, so back to the time that things every single thing was actually assembled from a little ball called atom. Okay, so back to the time we don't have the concept of electrons. We don't have concept of protons. Okay, so all things only become clear after a year. The J.J. Thomson, okay, he start to realize that okay, the atom thing is actually charged species. Okay, so instead like a big solid ball, it looks more like it's going to be influenced by the electric field or magnetic field. Okay, therefore he started to propose, okay, we actually don't have a ball, we actually have a sample of electrons and protons. Okay, that's why see the second picture is a lot of dots. Okay, rather than a solid ball. Okay. So this is actually get further improved after 7 years. The Rumford actually started to bring up the idea. Okay. You think that atoms is indeed a charged species. Okay, in the center part we have a positive charged species. Okay, then outside part we have this electron. Okay, and electron just actually circling around the nucleus. Okay, so it's actually very close to what we know right now. Okay, but things got further improved by Niels Bohr, which is actually one of the most important breakthrough of the nuclear field because it brings up the concept of orbital. Okay, so now everybody learn this 1s, 2s, 2p6. They count orbitals, right? Yeah, Bohr is actually the person who actually delivered all those theories. Okay, so after that, after another 13 years, a very famous thing called the quantum chemistry shows up. Okay, so the person who invented that is Schrödinger. Okay, so the difference between this Bohr model is that previously we think about the atom actually orbits around the nucleus by specific trajectories. Okay, but it turns out now the model that's more close to reality is that we just have a bunch of electrons, okay, surrounding by your nucleus. Okay, they just show up at specific location at specific time. Okay, there's actually a specific probability associated with that, and that probability that the electron will look like you have a certain orbit around the nucleus. Okay, so up to now, we still use this theory, and we use probability to describe where the electron will show up in respect to the center of the nucleus. Okay, so let's get to the evolution about the view of atoms from the very beginning, 1903 to 1926. Right? So people just spent around 25 years to complete the pictures. Okay, so what happened after 25 years? Do you feel like amazing that people can actually change things so much in 20 years? Okay, but from 1926 to today is 2025, right? That's 100 years, right? Nothing really changed. Okay, so at the time, it's really amazing how these scientists can actually figure out all these amazing models in such short amount of time. Okay, but this means that we are slackers. No, we also do a lot of research. Okay, things also change a lot. We actually find out there are smaller atoms. So this, the most one they go is actually they have this concept of proton, neutrons, okay, electrons. Those are three major particles that 100 of the physics they can actually comprehend. Okay, so nowadays we actually realize that those are not the three smallest particles. Okay, so they actually can make out even smaller particles. Okay, but those is not completely validated yet. Therefore, it doesn't show up in your textbook. Okay, so the recent scientist is still amazing. Okay, we create all these amazing tools allow us to see smaller and smaller and smaller things. Okay, but that's actually the basic concept that you should have. And today, I guess we'll actually finish the first session. All right, so how do you actually describe an atom based on all these models? Okay, typically the first thing to learn is called this atomic symbol, where you're going to see the big X in the center. Okay, on the top left corner, you have a symbol A, bottom you have the symbol B. Okay, so the X is the letter symbol. Z is the atomic number or the proton number. Okay, number of protons. The A is the total mass number, which is actually a sum of proton and neutron. Okay, so basic idea here you should have is that the nucleus is made out of proton and neutron, surrounded by a bunch of electrons. Okay, so how do you actually use this table? For example, when we write out zinc, okay, zinc itself is a letter symbol, okay? And after you write out zinc, then you can actually go to your periodic tables. So zinc is right here. So this, you see that little 30? That little 30 is actually the atomic number of the atom. Okay, 30 means actually you have 30 protons. Okay, therefore when you write out your symbol, you know you can write zinc and you write out 30 over here. Okay, so the bottom left, the 30 is the atomic number. That's also the number for your proton. Okay, the things on the top left will be the mass, okay, atomic mass that you get. And that mass will be determined by the sum of proton and neutrons. For example, if I say I have 31 neutron in this specific zinc, okay, then I can write this atomic symbol 61, zinc 30. Then to write this atomic symbol to represent a specific condition. Okay, meaning that the letter symbol is zinc. You have 30 protons. The overall mass is 61. And then you have 61 minus 30, which equals 31 neutrons. Okay, so that is actually the first thing that we need to learn. If I give you the number of protons, number of neutrons, then you write out its atomic symbol. Okay, that's the first thing that we learned. Okay, so for example, if today I say I have an atom who has 3 protons, 2 neutrons, then what will be the atomic symbol you're going to have? So you start from the protons, right? You have 3 protons, therefore you're looking for the species have 3 protons, therefore you know your later symbol will be lithium. Okay, then you write down the proton number, which is 3. And you can compute your mass number by add up the number of protons and number of neutrons, which will be 5. Okay, so if I tell you I have an atom contains a certain amount of neutrons, certain amount of protons, then you will be able to write its atomic symbol. Okay. Vice versa, if I give you an atomic symbol, you should be able to actually know how many protons it has, how many neutrons it has. Okay, so those are the first things that we need to actually learn. Okay. One very interesting thing that we see all the time in our daily life is called the isotope, right? What's the most famous isotope that you know? Okay, so I guess the most commonly seen is should be carbon-13, right? Carbon by itself should be 12, right? Often you don't see carbon-13, right? So typically we use carbon-13 to actually determine the age of substance. Okay, so this I will show you how you can use that concept to calculate, to explain how old that wood will be. Okay, so isotope is actually the things that have the same amount of proton, but different amount of neutron. Okay, so if you have the same amount of proton, therefore we have the same later symbol. Okay, but the mass will be different. Okay, if you have one extra mass, then those things will call it as isotope. Okay, so next level stuff here. Okay, we just quickly go through this, how you're going to write these things. Okay, so get yourself familiar with atomic symbol. Then we're going to tell you how to figure that in the next section. Thank you.
Yeah, that's true.